Yeah, hello, welcome to week six. So in this lecture, we will be focusing on flame atomic absorption spectroscopy, which is the most common and straightforward type of AS, where a flame is used to atomize a sample. Okay, so it has got wide applications in environmental, biological, industrial analysis for detecting metals at ppm as well as ppb level. Okay, so I'll just tell you about this. It's just flame AS. Okay, flame atomic absorption spectroscopy. And why FAS, if you ask, it's because metals are best analyzed when their solutions are directly aspirated into a flame, producing free atoms that absorb characteristic light from a glowing cathode lens. And aspirate basically means just suck a liquid solution into the nebulizer and flame using gas suction. So I write it in terms of words. Okay, so metals are best analyzed when the solutions are directly aspirated into a flame, producing free atoms that absorb characteristic light from a hollow cathode lamp. And what does aspirate mean in this context? Aspirate basically means suck liquid solution into the nebulizer. Using gas suction. Okay, so I'll just write more notes about this phase. I'll write fast from now onwards. If I were to put it in terms of a flow chart, so the solution you have, for instance, arsenic groundwater solution, convert it into a mist. Then you introduce it into the flame to release free atoms. On top of that, you shine your radiation. But that radiation should be element specific. Measure the absorption. So like this, you can measure copper, zinc, lead, iron, any metallic contaminant, cadmium, you or water sample or biological sample or food sample. Okay. So I'll write down the step-by-step procedure, okay, that we have to go through in AS. Just basically I'm recapping whatever sir has covered, okay? So just it'll be just theory through this. This is basically to warm up the hollow cathode lamp of the element of interest. Next is you take a blank solution and you aspirate it. I already told you what aspirate means. Basically it means to suck a liquid solution into nebulizer and flame using gas suction. So in this case, you just introduce a solvent. There should be no annihilate, okay? Right? You know what a nebulizer does, right? It converts it into mist. It should then take to a flame. So now since it's a black solution, there will be no absorbance, only transmittance, right? So that sets the best baseline. Okay. So next is you aspirate standard solutions. Standard means like they will be of known concentration, right? Say 5%, 1 ppm, 10 ppm, 100 ppm. Okay, like that. Every element will have its standard solution. Example, they're introducing arsenic, which are the arsenic standards. You have, like, you know the concentration, correct? The standard solution, say 1 ppm, 5 ppm, etc. And you will measure their absorbance. And after that, you plot the calibration curve. Calibration curve is basically absorbance versus concentration. Now you will aspirate the solution whose concentration you want to, if you want to measure. You set unknown solution to flame. Then for that, we will record the absorbance. Then we determine the concentration. So that we'll have to refer to the calibration curve. Okay, so we already put it earlier. Okay, when it comes to atomization and flame, okay, there are some terms that we have been using. I'll just define each of the terms once. Frequently came across this term nebulization, right? Over here, the solution is drawn into nebulizer, converted into aerosol buckets. Next is desolvation. So in this process, what does desolvation mean? It's like solvent is removed, right? So basically, solvent evaporates in the fluid. Evaporates in the fluid. Vaporization. Your analyte compounds turn into gaseous form. Ionization, thermal energy breaks your molecules into free ground state atoms. Then, of course, there is absorption, where atoms will absorb radiation of the hollow cathode lamp, lowering the transmitted light intensity. Okay. So parallelly, there can be many reactions in the flame also. Okay. If it's some compound, it can dissociate to its elements like CuCl will decompose into Cu and Cl. Then like new compound can also be formed, or the element can give rise to the ion also. Okay, and releasing an electron also. So this kind of side reactions also happen in the flame. Some additional notes about the flame chemistry and the flame environment. So basically, your temperature controls volatilization and dissociation, which is like basic common sense. One important thing to note is that atoms remain in flame only for microseconds for leaving the optical path. Okay, so basically, they are very short-lived species. They don't last long. Um, and if you say dissolve gold in seawater, in seawater, apart from gold, we'll have various kinds of salts like magnesium, sodium, etc. So those salts will also enter the flame and they can also affect your atomization process and the readings. Okay. So those are some things you have to consider when it comes to the flame chemistry and lava. So let us look at some of the interferences in ES. Can have spectral interference. Okay. So overlap of resonance lines of points is what is known as spectral interference. Example, resonance line, right? The first excited state electron. For example, uh, we have vanadium whose resonance line is 308.211 nanometer, and aluminum whose resonance line is 308.215. So you see, these are very close to each other, right? So there can be interferences because of this. So like, I can give an analogy like if you have an orchestra, okay, and two singers are singing almost at the same pitch, right? So you cannot separate between them, right? So that's what's happening with here. So likewise, you have magnesium, its resonance line is at 285.2 nanometer, and chromium 285 point just 203. Like it's 200. This is 285.203 nanometer. Very close to each other, as you see. So, so what other kinds of interference we can have? We can have something known as transport interference. Let's jot it down. What happens over here? So because of improper sample production, fewer or more atoms may reach the flame related to the transport properties. But there is something called, I'm not going into each of the details, but just keep in mind that you can refer to source notes for source lectures for all the details. There's something called solute volatilization interference for analysis loss due to premature volatilization. Can have a vapor phase interaction. which basically means reaction in the gaseous state or spatial distribution effects. Okay, so these are some of the other things. I'm not getting into the details. So the impact of these kinds of interferences is that absorbance may be lower or higher than expected, and because of which there is an error in the concentration measurement. Okay, so I already gave you some examples of spectral interference, right? There are many examples. You can just or get do your own research. That there can be interference between elements because of the resonance rate almost overlapping. Okay, so basically we talked about what FAS is, FAS is, what aspiration is, what are the procedure, what are the steps you do have to follow in this instrument. Okay, a little bit about flame chemistry, etc. So we have a short break, and after that we continue. Okay. Basically, we just between the lot of theory. We'll take a small break. Maybe, yeah. After this, sir went into details about all the interferences, so we'll also do that. Okay. Fine. So in this case, in this next session, I will next 20 minutes or so, I will look at some of the other interferences in more detail. So this spectral interference, I hope it is very clear by now. Okay, so transport interference is basically it happens when the aerosol particles do not enter the flame properly. Okay, so there is something called aspiration rate, which tells how fast the solution is drawn into the flame. And it depends on many physical properties like viscosity, surface tension, density, vapor pressure, etc. Okay, so I just write it in terms of words. Okay, viscosity, density, resistance, vapor pressure, etc. So I can give you some examples. So if you take high viscosity samples, okay, high viscosity basically means like they're thick. Like if you think of glycerol or something, it's much thicker than water. Okay. So what do you think happens in this case? Is the thick liquid pulled in slowly or faster? Or faster? So what does common sense tell you? Common sense will tell you that the thick liquid drawn in very slowly, right? And because of which there will be fewer atoms in the flame. What does that result in? If there are fewer atoms, the signal will be weakened, right? So if you have low viscosity liquid, say methanol, I think it's 0.8 or something of that of water, viscosity. This this will be drawn in much faster than the high viscosity fluid, right? So obviously there will be more atoms. This signal will be stronger. Oh. So likewise, if you have very high concentration of salt, So more the salts are, the droplets are bigger, and bigger droplets don't break into mist very easily, right? So fewer atoms reach the flame, and there is weaker signal. Okay, so high salt concentration. Example, seawater, right? Or you can even take blood or some biological sample like urine or something, right? So in this case, what happens is that the droplets are bigger because the droplets are bigger. They don't break into fine mist easily. Okay, so because of which there are fewer atoms in the flame, resulting in mixing. So if you're in case of organic molecules like say some complex polymer, some protein or sugar, there the solutions are a bit thicker. So in thicker solutions, one thing we already know that they are cooled in very slowly. Another thing is that they're harder to nebulize. So the weak signal will be very weak because of lower absorbance. But in case of some organic solvents, they burn very strongly because there is an exothermic reaction involved, in which case the flame becomes hotter, and hotter flames break the compounds into free atoms more effectively, resulting in higher absorbance. Right? So these are just some of the things. I'm not writing everything down, but I'm just telling you so that you get an idea. Right? So I'll just give some figures here. So if you dissolve your sample in 40% methanol and 60% HCl, the signal is about 1.7 times stronger compared to pure HCl, right? Because as you know, methanol low viscosity will be sucked in faster, more atoms, signal will be stronger, right? Similarly, 80% ethanol, 80% acetone gives 3.5% strong, 3.5 times stronger signal. Ethyl acetate can make the signal 5 times stronger, right? So you can add these kinds of organic solvents to improve the sensitivity of your instrument. But if they're already present in the sample, don't account for them because they will just act as interference. This was the transport interference. There is another thing called solute volatilization interference. So basically, what it means is that the element that you want to measure, right, the analyte, it forms compounds with other components in the sample, and this changes how easily it vaporizes and forms free atoms. Okay, so just write it in terms of words. You know what analyte is, right? The element that you want to measure. So in the flame, the analyte may not just become free atoms, but it may combine with other substances to form various compounds. It may be like oxides, salts, etc. So if the ensuing compounds are stable, so that means that fewer atoms are available. This gives rise to weak signal. But if those ensuing compounds are unstable, we'll have more atoms available. Strong absorbers. So some example to illustrate this, we have refractory oxides, okay? Example, chromium, vanadium, tungsten, okay? They form these things, they form oxides that are very stable, okay? Since they are very stable, they won't break down easily. You have very few atoms, few free atoms, because of which your signal will be weaker. Likewise, you can have ligand complexes uh, where they are bound very tightly to the metals, and because of which again fewer atoms are available and weaker. Another thing I already told you in the previous class is about the flame rate, which has got different temperature zones depending on the height above the burner. So if your sample contains sulfates, maximum absorbance occurs at higher flame height. But if it contains, say, chlorides or nitrates, maximum absorbance is seen at lower flame rate. So the practical, you have to be very practical in these situations. For instance, if you're analyzing sulfates, you have to raise the burner to sample higher in the flame. And for chlorides, nitrates, you have to lower the burner, right? Because maximum absorbance is seen. That also varies as a function of height. Okay. So observation height also matters. Sulfates, their maximum absorbance is in higher flame height. But for chlorides or nitrates, it's at lower flame height. And that's all. Okay, so likewise, in some refractory structures and polymeric cases, you'll have metals which form very stable compounds in the flame, okay? And those refuse to break apart into free atoms, thus reducing the number of free atoms available and reducing the signal. Okay, so I'm not getting into the details of all that. Okay, but you can give examples like ilmenites, perovskites, and whenever elements involved in titanium, zirconium, hafnium, molybdenum, silicon, etc. Because those compounds are very stable and the atoms get locked inside, because of which we have lower absorbance. Okay. The sir also talked about carbides and nitrates, right? The class, tungsten carbide or titanium carbide, they are very strong and survive even at 3000 degrees Celsius. Almost no free atoms and weak absorbance. Right? So, not getting into this detail. There is another thing called vapor phase interference. Okay, so these occur in the flame and chemical reactions in the gas phase shift the balance between free atoms and molecules. Okay, so I'm not getting into details of this. So just a definition for now is enough. See, flow rate and flow pattern interference is also something that we have to keep in mind because changes in the flow of gases and sample droplets into the flame that can also alter how efficiently atoms are formed, right? Because the rate of volatilization and size of particles entering the flame depend on the gas flow rate. So changes in the gas flow rate can create some changes, right? Because you can either trap atoms or freeze them. So that is another thing that you have to keep in mind. So yeah, keep there can be interference due to flow pattern and flow rate. So if I were to summarize, I'll just say that atomic absorption spectrometry is very powerful, but also highly sensitive to interferences. Solvents, salts, organic matter, flame chemistry, gas flow, all influence how many free atoms are produced. So you have to be aware of these facts so that you can get measurements that you can rely on. Okay. Yeah, take a couple of minutes. Okay, so moving on, we looked at the various types of interferences. Now there is something called background absorption. Okay, so what it means, it should be quite obvious from the name, right? So it's that part of the absorbance that does not come from the analyte atoms, okay, but instead from other sources. Like I told you, there can be other reactions with the flame, right? Molecular reactions, all these species can be formed. Okay, so because of that, there is a false absorbance which is which shows up. So what is background absorption? Part of measured absorbance doesn't come from net atoms. But instead, associates same gases, solvent, or multi-species form. Basically, not the element of interest to me. So you can have those same gases absorbing radiation. You can have molecular bands that are forming, molecular species form in the flames, right? So how do you correct it? So basically, because of this thing, can reduce the analyte signal or it can exaggerate or mask the true absorbance. So the correction method is use a reference solution without analyte and subtract its performance. Hmm. So problem with halocathode lamps is that they emit narrow element specific lines. Background absorption is usually broad and continuous. Okay. So a deuterium lamp is a continuum source producing radiation across a wide wavelength range, including the analyte's resonance wavelength. Okay. So this broad radiation makes it possible to measure and separate the background absorption accurately. Okay. for the problem of this background absorption. Okay. So the deuterium lamp, it provides a reference beam that passes through the flame but is not element specific. It measures only the broad, non-specific absorption due to background. By comparing the signal from hollow cathode lamp with the deuterium lamp, we can subtract the latter to isolate the analyte absorption. Okay, so how the radiation alternates between HCl and deuterium and all, like we use a rotating chopper and all, I'm not going into all those details. Okay, so basically you compare the signal from the hydrocathode lamp with the deuterium lamp and you subtract to remove the background radiation. So that's how this deuterium lamp method helps us. Let's write it at one point. Deuterium lamp. There is another thing called Zeeman effect method. Okay. So the principle between behind Zeeman effect method is that when atoms are present in a very strong magnetic field, greater than say 10 kilogauss, their electronic energy level splits into multiple components. And the splitting of spectral lines is called the Zeeman effect. Splitting of spectral lines when placed in strong magnetic. Okay, so without magnetic field, you have one sharp spectral line, but with magnetic field, the line splits into many components. And the background absorption is not affected by the magnetic field, but the atomic absorption lines from the analyte do split. So that is how it helps in background correction, because this difference allows separation of analyte signals from background. So this difference allows us to separate the analyte signal from the background. So again, there is mechanism of correction, like what happens when magnetic field is on, when it is off it. Like in one case only the pi component, which is a detector, in another case pi and sigma both reach detector. I'm not getting on to all that's all those details. Okay. So again, Zeeman splitting can be normal Zeeman effect, or it can be something called anomalous Zeeman effect. In normal Zeeman effect, three components. are seen. Nanometers more than three components. Okay, all that I'm not getting into details. So, so I'll just let you know that beryllium, calcium, strontium, barium, they have normal Siemens splitting. Whereas chromium, iron, molybdenum, they show anomalous Siemens splitting. So again, there are some things you can do on your own, right? It transfers and longitudinal Zeeman effect. Can take it as like self-study. Then there is something called Smith-Hive background correction. So this is another type of background correction which uses the phenomenon of self-absorption in holocathode lamps at high current. This also you can do like a homework. So in this case of Smith-Hive background correction, you basically alternate between high and low current every 5 milliseconds. So in case of low current, you will have normal AA spectrum, and in case of high current, the lamp line broadens and undergoes self-reversal. That is, the resonance line intensity is minimized, and you get mostly background signal. So you subtract these two signals, and you get the background corrected absorbance. So in this case, there is no magnetic field needed. Very simple design. So it's good for analysis where Zeeman systems are not available. Right? So interferences, you can also tell in terms of whether it's physical interference or chemical interference, following from what we did earlier. Like we talked about viscosity, surface tension, vapor pressure, and all right. So the size of the droplets, like large droplets fail to reach the flame, reducing the signal. Those kinds of things are physical interference. But what happens in the flame, right? Because of the flame chemistry, that comes under chemical interference. Or what happens in case of the refractory oxide formation, okay, or interference because of these compounds, etc. Or there can be ionization interference because at high flame temperature, atoms ionize, and this reduces the neutral atom concentration, giving lower absorbance, right? So you can also divide like that. Okay. So there are some practical considerations in AS. You always prefer nitrate salts over chlorides or sulfates for standards. Avoid acids that can form interfering species in the flame. You have to optimize the flame also. Optimize the burner height, aspiration rate, etc. Okay. So yeah, these things are. That's it for today. I'll end the classroom.